Yeah, thank you. Okay, cool. Yeah, we're excited to be here today. Yeah, just a quick intro. I'm Stephanie. I'm one of the creators of Ray, also now a professor at University of Washington. And this is Ray. He's one of the members of the Ray core team and a lead developer on the compiled graph system, which we'll be talking about a lot more later in this talk. Okay, so for today, we're going to go through a quick overview of some of the major features that have been released in Ray core since the last Ray Summit. And then we'll spend the rest of the talk actually doing a deep dive of this system called Ray compiled graphs, which you may have seen in the keynote. And this is essentially a new backend for the Ray core system. And so we'll do an overview of kind of the reasons why we built this and how you can use it yourself. So for those of you who aren't super familiar with Ray core is basically the AI compute engine that underpins all of the distributed libraries in the Ray ecosystem. So all of the things that all the libraries that you love using in Ray, from Ray train to Ray data, what underlies all of these is the same set of core primitives. And this is remote functions or tasks and remote classes or actors. And the backend for this API is Ray core. So this is a general purpose distributed execution system. And anytime you use a Ray library, you're really using Ray core. So there have been a ton of different features released since the last Ray Summit. So I just want to highlight a few of them here. We now have weekly releases, which is a really exciting development, going from 6 weeks, I think, on average per release before. We now also have support for structured logging. So this supports log format and also JSON logging on Anyscale. We have a ton of different stability bug fixes, and a lot of these are related to execution on spot instances. So you can expect to see better reliability in these cases. I'll also do a little bit more of a tech deep dive on two features, Ray generators, and some exciting developments in scalability of Ray clusters, going from 4,000 nodes at the last Ray Summit to now over 8,000 nodes today. So Ray streaming generators, what is this? This is basically the idea of taking a Python generator and now being able to execute it as a Ray remote task. And what's new now is that we support streaming behavior, meaning that you can actually consume object refs while the task is still executing. And this pattern is actually being used today already in libraries like Ray data and Ray serve. So one example in Ray serve is for LLM generation, where you want to be able to consume some partial results while the model is still decoding the rest of the sequence. And so just to give a quick illustration of this, the way that this works is that we'll have a caller process and the worker process that actually executes the task. And you can submit a generator task using the normal .remote syntax, and you get back this generator of object refs. So you can call ray.get on these object refs, and this will block as usual until the result becomes ready. So on the worker side, we'll start executing this task asynchronously. And once this yields the first result, we can now unblock the caller. And the caller can then do the same thing to get the next reference. And this will execute in parallel with the worker, and so on. And so in this way, you can see how you can actually put some work on the caller, and that will actually overlap now with the Ray worker execution. The other major development that I wanted to talk more about is scalability to 8,000 nodes. And so this is kind of a high-level overview of the Ray architecture. Typically, a Ray cluster will consist of some pool of worker nodes, which are homogeneous. They all look the same. And then one head node, which runs some kind of specialized cluster services. And these include the global control service. So this is a centralized service that runs a bunch of kind of cluster metadata management tasks. So that includes things like actor scheduling, placement group scheduling, and node resource availability. And we also have the dashboard server, which is maybe a lesser known process, but equally important. So this is actually used for a bunch of auxiliary application functions, not just hosting dashboard metrics, but also things like streaming logs from the rest of the cluster and supporting the Ray jobs API. So you can imagine that because these two services are centralized, if you design them naively and you try to scale out a cluster, you could end up, sort of linearly increasing the load on these two services, right? So through some great engineering work on the event loop that kind of underpins these two services, we've now made it so that even when the load on these services increases with the size of the cluster, it won't affect the availability of the services. And so this is one of the major features that has led to this improved scalability. Okay, so I'm going to switch gears now and talk a bit more about the Ray compiled graph system. And so I want to first talk about why we actually built this system. And so to do that, we're going to contrast it with kind of the classic Ray core backend that you may be more familiar with. So one way I like to think about Ray core is as kind of this programmable infrastructure that you can use for any kind of distributed compute-intensive tasks, right? So that includes things like data, training, and inference. But historically, the performance of Ray core at millisecond scale becomes a problem. And so here what I'm talking about is if you have compute tasks that run in tens of milliseconds or less. And so compiled graphs is a way of giving you a Ray core-like API, but with much better performance for cases where you repeatedly execute the same task graph, and also native support for GPU-GPU communication, which again is something that users have actually requested over and over again in Ray core, and we'll talk a little bit about why that's been difficult to support in the past. So today we'll talk about, do more of an overview of why we actually built this system, what the API is and how you can use it, and also some exciting use cases that you can actually build out with compiled graphs. So one of the major takeaways is that Ray compiled graphs are 10 to 20 times faster than Ray tasks run on the classic Ray core backend. And this is specifically for static task graphs. And you might be wondering, what are these cases? Well, a lot of multi-GPU workloads actually can be expressed with completely static control flow. And so later in this talk, we'll give some examples here in multi-GPU LLM inference, as well as some cases in distributed training. And if you're interested in more of these workloads, I'd also encourage you to attend these talks later in Ray Summit, which will do a deeper dive on both inference and training. Okay, so that I'm going to show a little bit more about why we actually built this system by first taking a look at why there are these overheads in the classic Ray core backend. So this is going to be just a quick example where we have, we're going to create these two echo actors, which just take in a message and then echo back the same message. So we'll create the two actors here. And then we're going to create just two tasks. So we're going to pass the message hello to actor A, and then pass that result to actor B. And just for the sake of this example, I'll also have the object store here. And so what this looks like is that we're going to pass this message hello to actor A by creating an object in the object store. And we're going to pass the reference to that object to actor A, which will then read from that object. And we have to repeat this same process when actor A creates its return value. So we'll return back the reference to the driver, which can then pass it to the actor B, and so on. And so you can see here that there's actually quite a few different arrows moving back and forth in this picture. And that's only considering the ones that are kind of on the critical path of execution. And so you can see very clearly here that the RPCs, especially to the driver, can become a bottleneck. And so this is exactly why we built compiled graphs. When we think about Ray core's classic API, one of the really great things about it is that it lets you create tasks dynamically. But that also comes with a cost, right? So it means that you have to pay the cost of doing these RPCs at runtime to execute the task. You often have to do some kind of dynamic memory allocation to pass around arguments and return values. And it's also very difficult to support peer-to-peer protocols like NVIDIA's Nickel protocol. And that's because these kinds of communication patterns require you to actually allocate resources upfront on all peers. And so in compiled graphs, the idea is to take static task graphs, which you can express with a Ray core-like API, but instead of allocating resources dynamically, we can just allocate them once and then reuse them for multiple executions. And the other great thing about this is that it now also lets us declare these kinds of peer-to-peer communication edges up front. And that way we can schedule them before the execution actually happens. And so just to give you this picture, what we want is to go from something like this to something more like this, where the only communication that's happening is kind of along the path of the data. So to show you the API and how this works, I mentioned there are 2 steps, right? So first we need to compile the graph. And so we're going to now, from the user side, we're going to declare what the task graph looks like. And this is actually the same kind of task graph that we had earlier, except now we're going to bind to an input placeholder instead of binding to a physical input. Next, what we can do is add this new compile command. And under the hood, this is going to statically allocate the resources. So we allocate some static buffers in the object store that can now be reused across multiple executions instead of just once. And we're also going to start an execution loop on each involved actor that will know basically the tasks to execute at runtime. And that way, during execution, we can kind of avoid those expensive RPCs. So now when we actually call execute on the graph, we're just passing in the input from the driver. We can also use the normal ray.get API. And what this looks like during execution is basically just the path of the data. Another nice thing that we can do in this API is support exception handling that gives you a very similar experience to normal Ray core. So the idea here is that for application level exceptions, let's say actor A throws maybe a Python value error. What we can do is store that result in the object store. And that way we can actually throw it to downstream tasks and even to the driver. And this is just like normal Ray core. For system level exceptions, so there are certain cases that we can't recover from. So let's say this actor A dies. In that case, we actually can't produce results anymore, right? So what we can do instead is just tear down the DAG resources. So we can clear away the objects in the object store and also stop these execution loops. And one really nice thing about this is that you're kind of just back in normal Ray core land. You can reuse these actors that are remaining and potentially compile a new graph. All right, so I'm going to hand it over to Ray to talk about some of the primitives that are specific to GPU programming.
Hi. Thanks, Stephanie. Next, I'm going to talk about how to use Ray compiled graphs to program across multiple GPUs. Suppose we have a sender actor that runs on GPU 0, and we have a receiver actor that runs on GPU 1. And the sender needs to send a tensor to the receiver. Compiled graphs could send this through shared memory, just like Ray core. But it also adds the support for direct GPU to GPU transfer through Nico. And the way to achieve this is really simple. As we can see from this code snippet, we can just take the output of the send method and annotate with a type hint, that is the torch tensor type, and we specify transport equals Nico. And then we pass this to the receiver, and that's it. The rest is the same as Stephanie just talked about. We compile and then execute. Other than the point-to-point APIs we just talked about, compiled graphs also support collective APIs. To illustrate, we will use all-to-all pattern as an example. That is all reduce. So in this example, we have a few workers, and each worker has its partial data. And we have this, we put this data, the references to this data to a list called parts. And then we can simply call read.collective.allReduce on the parts. And that's it. Here, we also use transport equals Nico group handle instead of just the string Nico. And this allows us to use a previously defined Nico group for the communication instead of using the default one. We also support other patterns like all-to-one and one-to-all. They have a very similar API. A common problem for GPU to GPU communication is the possibility of a deadlock. This is because Nico operations are blocking, and it could deadlock if execution has circular dependencies. Let's look at an example. Say we have two actors which use Nico to communicate between their tasks. Underneath, compiled graphs adds this Nico send and receive operations to the corresponding tasks. And we can see that there is a circular data dependency between the actors, as shown with the red arrows. And this could lead to deadlocks during execution. Our solution is to generate a schedule at compile time. The compiled graph generates the schedules for all the actors with global ordering with topological sort. And then it schedules the Nico operation pairs, for example, the send and receive together when there are no other data dependencies. Compiled graph supports overlapping GPU communication and computation for better performance. Suppose we have a trainer actor that first runs a forward task and then runs the backward task. This task use Nico receive and send communications, so we have these operations. The default, the naive approach would just run them with a single CUDA stream. But compiled graphs optimizes this by using multiple CUDA streams and leveraging a scheduling algorithm to overlap the communication and computation. As a result, a receive stream, a computation stream, and a send stream are used, and these operations run on different streams and can be overlapped. As we can see that the receive operation and the forward can be overlapped, and backward and send can be overlapped. And this reduces the time to finish the execution. We evaluated the performance of recompiled graphs compared to recore. For a simple round-trip benchmark, compiled graphs is 17x faster on a single node and 2.8x faster on multi-nodes. And the difference is larger if multiple tasks are involved. For example, if we do scatter and gather of 32 tasks, compiled graphs is 18x faster. And if we chain 32 tasks, the compiled graphs is 21x faster. So to summarize, compiled graphs is 2.8 to 21x faster. As for Nico operations, compiled graphs has no overhead for static shaped tensor. And for dynamic shaped tensor, it has roughly 0.5 milliseconds overhead because compiled graphs needs to send additional metadata transfer through shared memory channel. But we are working to improve this. So after talking about the APIs, what can you actually build with compiled graphs? I'm going to talk about a few examples. And we will start from distributed inference, specifically optimizing the VLM control plane. This diagram shows the VLM control plane architecture. So there's a driver that runs the LLM engine, which sends the request to multiple workers that execute the different model shards. And previously, when Ray was used, the overhead was 2 to 3 milliseconds for the communication and the serialization. When we use compiled graphs, the overhead is about 100 to 200 microseconds. And with compiled graphs, we have reduced the latency for distributed inference. We also implemented tensor and pipeline parallelism with compiled graphs in VLM. As you can see from the core implementation, the code is really short. And from a high level, what this does is, the compiled graphs takes the request as the graph input. And then for each tensor parallel group, the workers just execute the model, and their output are transferred to the corresponding workers in the next PP stage. We measured the VLM performance when using compiled graphs, For online inference where the latency is important, we achieved a 10 to 20% reduction compared with the original architecture. And for offline inference where the throughput is important, we achieved a 10% improvement. We also achieved the performance parity in various other setups. Note that this comparison is between a very simple compiled graph implementation and the continuously improved VLM implementation. So this highlights the compiled graph has provide good performance even without manual optimization. Compiled graphs also provide great support for heterogeneous training. So in general, there are two types of distributed training. One is homogeneous training, that every process executes the same program. And examples include data parallel, fully sharded data parallel, and tensor parallel training. For heterogeneous training, different processes execute different programs. Examples include pipeline parallel and when we use heterogeneous clusters. Recompiled DAGs lets you easily express and scale the heterogeneous training. So for pipeline parallel training, compiled graphs allows you to express various pipeline schedules in less than 100 lines of code. As for multimodal training, compiled graphs allow you to run different training components, for example, the vision and text encoders on different types of GPUs, which can help to improve GPU utilization. To summarize, we covered two classes of applications for compiled graphs. One is distributed inference, and another is heterogeneous training. We covered this from a high level, but there are two additional talks for this. One is the multi-GPU inference with VLM. The other is beyond FSDP talk. The first one is today at 4 p.m. The other one is tomorrow at 1 p.m. And I highly recommend attending these two talks for more details of how we exactly implement them with compiled graphs. Next, I'm going to hand this back to Stephanie to talk about what's next.
Okay, cool. Thanks, Ray. For Ray compiled graphs, the next step is to release the beta version, so keep an eye out for that. Some of the major features that are in progress for this right now, Ray actually already mentioned a couple of these, but a lot of these are around improving support for GPU tasks, especially improving performance. And these will be directly leveraged in the end use cases, including VLM, where we're currently working towards an architecture migration for VLM's control plane to make Ray compiled graphs the default for Ray VLM on Ray in the future, as well as exploring some more complex architectures like prefilled disaggregation. On the training side, we're going to continue kind of building on the heterogeneous use cases that we've seen so far and just further try to improve, have an excellent usability experience in addition to performance. So what's next for Ray core at large? So we talked a lot about Ray compiled graphs and how that builds on top of the Ray core primitives. Underlying all of this is Ray clusters, right? So you often will have a cluster of VMs that actually execute the Ray core system. Now, historically, it's been true that whenever you build a Ray application, you often need to create its own Ray cluster just to host that application, which can really be a problem, especially if you're talking about expensive GPU resources, where you might want to share these GPUs across different Ray applications, right? And so to better support this, we're excited to announce a new feature, a new feature in the future of Ray core, which is called virtual clusters. And the idea here is to basically allow you to take a single physical Ray cluster, so just one head node here, and be able to slice it into multiple virtual clusters. And so basically what this will let you do is actually use all of the normal Ray scheduling primitives, but within kind of this now virtual container of Ray resources. And so hopefully in the future, this will now allow us to efficiently share resources between jobs while also enforcing resource isolation between those jobs. Okay, so today we talked about some of the exciting developments in Ray Core towards its both present and future as an AI compute engine. And yeah, we're happy to take any questions. Sure. Yeah. Oh, yeah. You can.
Question regarding the benchmark between Ray Core and compile graph. It seems like the single nodes significantly better compared to the multi-node scenario. Can you explain what was the intuition behind it, and is there any plan to improve the multi-node scenario?
Sure. Yeah. The question was about the benchmarks for Ray compiled graphs versus Ray Core. Okay, maybe I was going to see if I could pull up the slides, but I think it's too hard. But yeah, so there was this kind of big gap on single node performance, and then for multi-node performance, the gap was not as large. So the question was why? Do you want to take a shot? Okay. Well, yeah. So basically, right now we've actually focused primarily on single node performance, especially thinking about kind of multi-GPU inference use cases where you often have multiple devices on a single node. And so basically, what we've done is kind of leverage the shared memory object store to really improve that case. And so essentially, what you can do is kind of eliminate all RPCs on the critical path for single node execution. For multi-node, whenever we cross a node boundary, we still have to use RPCs right now, and we're just using kind of vanilla gRPC for that. That's definitely something we would like to improve in the future. So, you can imagine actually using something like RDMA, for instance, to further improve that. Yeah. I think maybe you were next.
I have two questions. The first one is, how does this interact with RayTune? Is there an integration with RayTune?
RayTune, you said?
Yeah,
so the question was, how does this interact with RayTune, and is there integration with it? So today, there's no integration with RayTune, or actually with any of the other Ray libraries for that matter. So in the future, we'll definitely think about how we can actually integrate these directly into Ray libraries. But for now, we're kind of focusing on sort of the multi-GPU use cases that have not been supported well yet by Ray Core. And those are specifically VLM and some of these kinds of heterogeneous training cases.
My second question was, maybe it's a different use case, but we care a lot about reproducibility. And do you think it could be in the future possible to save the compiled graph to ensure that you have reproducible training?
Yeah, so the question was about reproducibility and what we can do in compiled graphs to better support that. I think that's a great point. Actually, yeah, I think one of the values of the compiled graph API, we hope, is that you get actually better predictability, right? So, if you run the graph once, you know that you're going to get the same performance for every kind of future execution. And yeah, I can definitely imagine taking that further and actually being able to kind of save the compiled graph as an artifact. Yeah. Yeah, maybe you? Yeah. Yeah, so the question was how this relates to LLM training frameworks like Megatron or DeepSpeed. Do you want to? I can.
Yeah, sure. Yeah. So I think we have actually in our applications we actually use CompelDex to compare with DeepSpeed specifically, and we achieved performance gains because of our the performance optimizations in compiled graphs. And actually, there's a talk, like I pointed out, that talk that we'll have a deep dive on that specifically. I recommend you going to that talk for more details.
Yeah, I think I'll also add that as of today, there's no kind of end-to-end training solution built on top of compiled graphs. That is something that we're kind of thinking about for the future, but at the moment, the goal is actually to take kind of the cases that we don't think are supported as well in Megatron and DeepSpeed and frameworks like that, so especially these kinds of heterogeneous use cases, and try to see what performance we can gain in those scenarios. Yeah.
So going back to the failure case for compiled DAG where like a node fails or something, what does the user see that is
Yeah, so the question was about the failure case where a node dies. What does the end user see? So again, this is a little bit of a work in progress, but the thing that we would like to support is basically to be able to get a system level exception on the driver as you would in any case. We already have that today actually, but what you don't get as good of an experience on is kind of the root cause. So you can imagine it'd be great to know actually that the root cause was that this particular actor died. Yeah. Maybe over there? Yeah. Oh, so the question was, are you asking about scheduling overhead? Yeah, so I think the question was about if we introduce this kind of virtual cluster concept, won't there be performance overhead from that? Yeah, so that's probably a topic of further discussion. You can find me offline, but basically we think that we can kind of avoid that by doing it and kind of, it's basically what you can do is just support using the same scheduling mechanisms that we have today, but essentially you just add a filter first to filter down to the virtual resources. Yeah. Yeah.
I think one thing you can do with data execution is that you can do a lot of optimization because you know what the execution will look like. But those strategies are highly dependent on the different scenario. So the compiled graph will do some general strategy, or it will depend on the certain scenario.
So I think the question was about what optimizations we can apply in a general scenario. Yeah, so this is still, an open question of what, basically how specialized can we be to the application. But we think that there are certain optimizations that are really common, Ray talked about overlapping compute and communication. And these are things that you can apply actually without really needing to know much about the application. So those are the kind of cases we'll target first. Yeah, is the compiled graph system engine agnostic? And yeah, so right now we are working primarily with VLM, and that's because VLM was already built on top of Ray, and they were seeing issues with Ray core and the performance overheads from that. But it's not, there's nothing about it that is VLM specific. So definitely you could integrate it with other LLM engines like SGLang. I think really the requirement would be that right now at least you need to be using Python. I should also say we're supporting Nickel just as the kind of first step. But actually, Ray actually already kind of has support for being able to do these custom communicators. And so our goal is also not to be kind of specific to a particular hardware platform. Yeah. Sorry, what was the question? Yeah, what is the current support for RDMA? Currently, there is no support, but that's definitely something we're interested in supporting in the future, especially for these kinds of control plane messages. Yeah. Sorry. Oh, yeah.
Do you have an option to, when compiling graph, do you have option to optimize for throughput or latency?
Yeah, is there an option to compile for throughput versus latency? That's an interesting question. Right now, we don't have anything, I would say, that's specific to those two regimes. And actually, we're using the exact same system for both training and inference. But yeah, in the future, there might be cases where you would want to do something different at compile time. Yeah. Yeah.
Do you have any optimization strategy, like data caching, using object store and other stuff for optimizing throughput?
Do we have any optimization strategies based on data caching in the object store? Is that the question? So I guess in a way, the system actually is kind of designed around that concept because we use the same sort of shared, like the same physical memory over and over again. So you can write different data to it, but you'll use the same physical memory. But we don't have anything related to kind of like a higher level concept of data caching. Yeah. Yeah.
Do you think the big data backend is going to be replaced with data, or the data is going to continue to depend on the regular record?
Yeah. Do we think that Ray Data's backend can continue, could be replaced by Ray compiled graphs, or will it continue to use Ray core? Do you want to answer it like this?
Yeah, I think that's definitely an interesting question, and we are exploring. I think right now, like there's just some early work, but it's not decided yet fully.
Yeah, I think also, it's like our goal is actually for this to work well together with Ray core, because there are definitely things about this that, Ray data is actually an extremely dynamic workload in many cases. If you're using it for batch inference, there can be kind of static parts to it, and those could definitely benefit from this. But by and large, a lot of it is actually dynamic. So ideally, you would want, I think, some combination of both.
It would be like a mixed hybrid kind of graph where certain parts are static and certain parts where the dynamic parts just go on to the core dynamic parts, but the static parts just go to the breakout parts.
Yeah, potentially you could imagine a future where you have some kind of hybrid graph and parts of it are dynamic and some parts of it are static. Yeah. Yeah, but we're probably a bit a ways from that right now. Yeah. Oh, okay. Okay. I think we are out of time. Sorry. Okay.